right, good afternoon. Sorry I'm a little late here. Seems like everything's a little bit late, but for me today, and I'm just moving along a little faster because of that, except that then got caught up on something and did that one last email 5 minutes too long, so apologize. But here we go. Today we're going to talk about mass balance equations as it relates to the acid-base kind of equilibrium problems. Again, we're looking towards how to find a solution for a solution, right? Kind of funny to say it that way, but we're looking to be able to set up an equation that can give us something like, what is the pH given that we have X amount of this acid and Y amount of that other acid and Z amount of this base and so on, right? How do we find a solution for what's all in this solution of water? So I'm gonna kind of start on that broad picture again for a moment to point us back towards kind of what we're looking at. Then next time today we're going to talk about the mass balance side of it. How do we describe the fraction of a given acid that is in one form or the other, or any species really? Derive these alpha fraction things, which is a fancy way of saying what fraction of a given species is in this form. And then next time we'll kind of put it all together and say, okay, here's these electroneutrality equations, here's this type of stuff. And we're not necessarily going to solve it all the way in this section and on this first exam, but we're building up these tools, and I want to make sure you're comfortable with the fundamentals of each of these tools, right? That's kind of my target. So that then for the next section of the class, we'll get into this graphical solutions. How do these come together when we graph them? We might have a MATLAB assignment to say, okay, hey, graph this, look at it this way, write a little program that can plot it for you. Maybe do that in Excel, maybe use Excel Solver to set something to 0 and check which pH, try to find the pH that optimizes the closest we can to get to that 0. We'll talk about that a little bit today as well. So we're going to move forward into that, but right now what I want to do is just make sure that we're understanding where the pieces are coming from. And so the first exam will kind of cover that. Can we find an alpha fraction? Can we use an alpha fraction within a relatively simple equation? And some of your homework problems should kind of show you that type of direction. Okay, so considering some generic acid, HA. A is the acid, H is the proton that comes off, making it acidic, right? This could be HCl, this could be HOCl, that's hypochlorous acid, all sorts of things. Acetic acid, we could abbreviate HAC, but the A there is standing for whatever type of acid we have. So for a given acid, there's going to be 4 species in solution. When we make some water, we're going to have OH minus and H plus. Of course, H2O will also be there. That's kind of assumed, and we're really kind of neglecting that. Otherwise, there's going to be A minus and some HA. Okay, so that's 4 unknowns, and for that system, we would need 4 equations, right? 4 independent equations to solve that problem. And so what we're dealing with today is going to help us get most of these. Of course, we're going to go, we talked about these last time, and next time we'll go into more depth on this part. But for the moment, we can recognize, and I'm just going to walk us through these real quick, the simple case, Kw, this is that mass action type of equation for water. So we know we have some K value for water, 10 to the minus 14, that describes that for water. So that's one equation. The second would be the Ka equation for our acid. So given some constant for our particular acid that we have this time, that's another mass action equation. It's independent from the first one, even though it's the same type, because it's a different species, right? And we have a different K value. Okay, then third would be the mass balance equation. And here's where our discussion today is going to give us more info, okay? So this will be largely today's stuff. And the last one, we've already talked about it, and in the simple case, we can see it's kind of obvious, but the last one will go in more depth in the next lecture, the electroneutrality equation. If we put all the cations on the left and all the anions on the right, we can set it up to be equal to, say, H plus is equal to A minus plus OH minus, right? Of course, if we had a 2 plus or a 2 minus charge, we're going to have to account for that, so we'll deal with that next time. But you can kind of see then we have 4 equations for the 4 unknowns if we have no information about any one of these. Now, sometimes in reality, we will have some information, let's say about H plus and OH minus if we have a pH probe. Those are pretty cheap, or even some pH paper. We can detect, okay, we're at pH 8. So therefore, we know the H plus and the OH minus, and then it becomes a lot easier. We don't need nearly so much in so many equations to solve our system. So just kind of a little reminder there that a lot of times we can simplify or perhaps do a more complicated problem with more stuff in it. Okay, but does this make sense? This is sort of the big picture where we're heading. Okay, and we'll come back a little bit to that bigger picture discussion in a little bit. So for the mass balance equations, what we're really saying is we have some conservation of mass, and in particular, we're going to hone in on a given acid or a given species that has some dissociation. And we're going to start with a generic equation for that and combine it with the other equations later to solve a more complicated system. So I'm going to give a few case examples. First is pure water. The mass balance on pure water. You might be thinking, well, water is water, right? Okay, so let's read this. It says when water dissociates according to H2O is in equilibrium with H plus and OH minus, there's a one-to-one relationship between the amount of H plus and OH minus. Now, in absolutely pure water, that's just the way it is, right? There's going to be as much H2O has dissociated, there's actually going to be equal amounts of H plus and OH minus because that's the only source of either of them. Now, obviously, as soon as we open this up to the atmosphere and there's CO2 or anything else it touches and something else gets in there, this could change. But absolutely pure water, no CO2 or anything, there's equal amounts of H plus and OH minus. So our mass balance could simply look like this, right? So pretty obvious, and that's also our electroneutrality equation in that system. Okay, so technically that's a mass balance. That's the pure water. Well, let's go on and say pure water with some generic acid, HA. So the mass balance here, we're going to be looking at the involvement of that A in particular. And so we're going to say that the HA is going to dissociate. So HA will be in equilibrium with H plus and A minus. And when that's the case, we're going to have H plus, we're going to have A minus, and the mass balance is to say that the total amount of A in here is, well, A minus plus HA, right, on a molar basis. So no matter how much is in the HA form or the A minus form, the total will be there. And we often will abbreviate this as AT with a subscript T, so for total. So the total A. We could write this as, let's say, OCl total or SO4 total, or whatever we have, whatever we might want to write there, PO4, whatever the case, that would be kind of what we're talking about. Usually we're going to keep it pretty generic and say A total or X total here. Okay. So that one's pretty obvious. Now, the alpha values, which we're going to spend some time elaborating on, would be, well, what portion of the total is in one or the other form? And usually we're going to use the alpha, the nomenclature as how many protons, we're going to put a subscript after the alpha to say how many protons has it given up. So alpha 0, well, maybe I'll say alpha number sign, if I can write it. The alpha itself is meaning the portion of the total. And that little number sign should mean the species that has given up or given away, we'll say, that number of H plus of protons. So when I say alpha 0, this is the fraction of HA. Because HA has not given up any protons yet, right? That means alpha 1 would correspond to the fraction of A minus. So if we have what we'd call a polyprotic system with multiple protons, like H2SO4 has 2 protons, or our phosphoric acid has 3 protons, we could have alpha 0, 1, 2, and 3, potentially up to 3. Or more if we had some substance with more than 3 photons. Okay, does that make sense so far? All right, so then this nomenclature then, the alpha, is really just saying, you know, so alpha 0 would be equal to the concentration of HA divided by the total concentration in the system of A. Okay, that's really all we're saying. And alpha 1 then would be A minus. Let me make this a little more separate. Okay, so pretty straightforward there. Where we'll get into a little more complexity is when we start substituting pieces in order to simplify, because these values are going to depend on the pH in terms of acid base at least. We can actually get these in terms of Ka and the current H plus concentration. So that's pretty handy because the Ks will be constant and the pH is probably what we're solving for. So we can get them in a way that we're going to solve for our unknowns. Okay, so this is the alpha fractions. We're going to come back to that, derive more of the alpha fractions. Just wanted to kind of make a little side note as we go forward there. So a few other cases for the mass balance, the generic mass balances. What if we have something that instead of a proton, we have a sodium or potassium or something, right? We can think of lots of different chemicals. For example, we can have hydrochloric acid, HCl, or sodium chloride, our table salt, right? And so if we substitute an Na there, well, suddenly our mass balance is a little different. If this is the only source of our A, say chloride or sulfate or something, if that's our only source of it, then the total amount of sodium in solution, in this example, is going to be equal to the total amount of acid, because that's the only form we added it in. There's no other sources for our acid aside from what was connected to the Na. So that's the assumption here, and so our mass balance becomes, well, one of the mass balances is the sodium is equal to A total. Okay? Another thing we could say is if we had a diprotic acid, so B having H2B, this would be the next case to look at. We could say H2B is very similar to the prior case, case number 2, I guess. We would have H2B, we'd have HB minus, and B2 minus. And the total of all of those put together would be our B total. Okay, so this is a lot like what we said a minute ago. So, and we could also label these as, or recognize that these will correspond to alpha 0, alpha 1, and alpha 2. By the way, we should recognize that if we take alpha 0 plus alpha 1 plus alpha 2, that should be exactly 1, right? Because the total amount, if we add the fraction that is in the first kind plus the fraction that is the second kind plus the fraction of the last kind, it should equal 1, right? The total fraction is 1 out of 1. 100% of the acid is in these forms combined, right? That would be the same thing on this one, right? So alpha 1 plus alpha 0 should equal 1, 1.0, right? Okay, so the mass balance in this fourth case here, this H2B, we're just recognizing that those protons can come off one at a time. So there's 3 different species that can be there, right? And we've already talked about this a little bit with the carbonic acid system, right? We could have H2CO3, we could have HCO3 minus, and CO3 2 minus, right? So this is a lot like H2CO3 as an example, where CO3 is B. Let's say like that. Okay, makes sense? All right, next case, sometimes we might add something like sodium bicarbonate, where we have another sodium here, could be potassium or whatever, but we'll use sodium, NaHB. So the B is again a 2 minus charged species, and our example could be sodium HCO3, so sodium bicarbonate. And here, we actually have basically the same thing as the case 3, where the amount of sodium added on a molar basis is the same amount as the B that we've added, right? B total is going to be equal to the total sodium. That's in addition, by the way, the separate equation that we can write is to say B total also equals the concentration of H2B that's there plus the HB minus plus B2 minus. Right? Both of those are true. And maybe I'll write that on the previous one also. And in fact, we already covered both of these, so I'm just being a little bit redundant pointing this out. But you kind of get the picture, right? We can take from the previous case of what is A and the mass balance on A and recognize that if we add it as a sodium salt or something like that, we have a little more information. Again, this is in a simple case where we have pure water and then this stuff, right? If there were other sources of sodium, we get into a little trouble or a little more complexity there. So maybe we could check the sodium before and after or something like that, but we're keeping it simple here for these cases. Okay, so next up, we could have a scenario where we have Na2B. And now it complicates it a little bit because for every one B that we're adding 2 sodiums. Otherwise, it's practically the same, right? The same B total here applies, right? So this is also true for this case. Anytime we have B that's a 2 minus charge, maybe in equilibrium with H2B and HB minus, all that's still true. Yeah.
So for the summation of B sub T, the first element is H2B, but I'm just confused why it's not NaHB.
Okay, so NaHB, when we put NaHB into water, our assumption is that this is going to become Na plus and HB minus when it hits water. And then we have It's a very good question here. So the assumptions are that that's going to dissociate, and then we are not having any reassociation with the sodium. That part should be a one-directional reaction. So NaHB, we are kind of assuming that this dissolves completely or dissociates completely, and then we have equilibrium between H2B with H plus and HB minus, and then HB minus will be in equilibrium with H plus and B2 minus. So we're never addressing the NaHB again because we assume that the sodium has come off and there's no molecules hanging around in solution connected to a B anymore.
And you're making like further equilibrium reactions like based on a conjugate base. Like you're dissociating the sodium and you're retrieving that's a conjugate base, right? And then you're using its procellary acid, right, to like make the equilibrium and then show it that way.
So once we have the HB minus, the B is what we're focusing on, right? B is the species, which is our acid in this case, and it's going to give or accept protons. And of course, if it's going one way or the other, then you might start calling it a conjugate base if it's given it up or whatever. But just a little more simply, we're going to say B is this acid, generic acid that can be in the H2B, HB minus, or B2 minus form, and it's in equilibrium with those three states. Okay. Again, a good example of this is the carbonic acid system. You could add sodium bicarbonate, and in fact, if you've ever done like the vinegar and baking soda thing, you probably have done just that. That bicarbonate is probably sodium bicarbonate or bisodium carbonate, and that's essentially what you're doing is you're adding it to water and it dissolves and your sodium is no longer attached. It's just not happy to stick there, right? Maybe there's some chemistry we could talk about for certain things. We could maybe consider it being combining with OH. That's also not very likely, but we could imagine a case like that. But right now we're just focusing on the acid side of it. That piece wouldn't be relevant. That answer your question, or are you still?
Yeah.
Okay. I think you might just be thinking a little more deeply than we need to at this point, because we're just going to keep it simply defined that B is this diprotic acid, and those are the states. Okay, but it is a good thought, right? Like why does Na not show up anywhere in here? Okay, so then if we add Na2B, the real difference here is that we're just simply getting a different stoichiometry. We have 2 sodiums for every 1 B. You can tell just by looking at this, the amount of acid we're adding has also changed, right? We are no longer adding an H for every molecule of the stuff that we're adding. So this is going to be a more basic form of the stuff. And in fact, depending on where these pKa's are, this could increase the pH, so make it more basic, just by scavenging some protons. Some of this will become H2B and some of it will become HB minus. We'll look at this more later in the next lecture, but that means we're taking some protons away from the solution. And so suddenly they are now in these other forms and there's less acid around. Okay. Regardless, though, for our mass balance, this is Na2. We can set our B total to be 2 times B total is equal to the sodium concentration, or of course we could write this as B total would be the sodium concentration divided by 2. Okay. Making sense? All right. Pretty much algebra, but we just have to know what's happening, what's going on, and what's not going on to some extent, right? About these species. All right, so I've got a example problem for you to solve. So I'm asking you to write the general mass balance equations for a solution of some initially pure water plus NaCl. And I'm going to give you most of the solution so that we can kind of see the discussion, and then we'll just reveal the answer in a minute. So give it a moment, and then in about 30 seconds, I'll go ahead and read this with you. But just think about it. What are those solutions before reading the text? Don't read this yet. Okay, so I'm going to read this and then let you have another minute to write something down. So if we dissolve some pure sodium chloride in pure water, the salt crystals carry no H plus, no OH minus that would alter any balance there. So technically, that first equation that was very simple, H is equal to OH minus, is one of them. And then we don't normally tend to write that, but we could use it. Then the mass balance equation is next. So Cl minus is what we'd call a spectator ion, just like Na plus. And that kind of goes back to what I was trying to say earlier. It's sort of there as a spectator. Once we put it in solution, it's just going to not interact with much. It's just going to watch what happens. So Cl minus and Na plus. And they have a one-to-one relationship, so it becomes pretty simple. So take just a moment longer to think about what that looks like. Okay, so this one was pretty simple, right? Now we can also, so Na is equal to Cl. That's the most obvious one. We could also, as it said, write that H plus is equal to OH minus. All right, let's do something a little more interesting. Oh yeah, you have a question?
Oh yeah, for that last one I did like Cl total. I did that one, but I also did Cl total equals HA plus Cl.
Yeah, and since we've been talking so much about HCl, that's a great point. We just talked about the HA system where I was using an example of HCl. I'm going to come back to why this is not the best example I should have been using, but you would be totally fine to say, well, if Cl is A, then you could say the Cl total is going to be, or just even call it A total, right, would be the Cl minus plus any HCl. That is also definitely true. And the reason that I'm telling, I kind of gave a bad example a little bit, is because HCl is such a strong acid that HCl itself is close to zero. Of course, it's not truly zero, but at all pH ranges, it's so strongly dissociating the pKa's. You'd have to go to a negative pH in order to get a 50-50 amount of it to find equilibrium with that. So that's why the book here is calling it a spectator ion. The same is true for the Na. On the other side of things, that NaOH is also a thing, but for the same reasons, it's such a strong base that we almost see none of it. right? Practically speaking. So you're not wrong there. And it's totally fine if you have written that, but it's just approximately 0 and it'll be a spectator. So because Cl minus is just going to be the only thing there. So a very good point there. When I gave the example of, let's say, HOCl, that's a better example because the pKa is a more neutral one. Okay, so let's take a look at this example then. We have 10 to the minus third formula weight of sodium chloride. That's just treat that as molecular weight. This is the formal way to describe it if it's going to dissolve, but we're first calculating it. So this just means 10 to the minus third moles per liter of NaCl was added. But as soon as we add it, it dissolves, so it's no longer NaCl, so the book's just being fancy and saying formula weight. And 3 times 10 to the minus fourth moles per liter of acetic acid. And that acetic acid we're going to call as HA. These are placed in 2 liters of initially pure water. And I think maybe the formula weight, that's if it was in 1 liter, so we might have to divide that. We'll check on what the solution says, bless you. So the solution might have us divide by 2 there. But okay, regardless, for this solution, write the general mass balance equations and the corresponding specific ones that you can consider. And I think the general ones would be a little more like, you know,
like using HA instead of the actual acid.
Exactly. That, and maybe the book is more describing like Na is equal to Cl minus, Na plus is Cl minus. But I'm not sure, so we'll see what the solution says. just write the ones that you can think of that we've talked about. Or perhaps it's specific meaning with the numbers. That's probably it. All right. I clicked it and didn't even realize it. So it's just been sitting there, huh? Okay, so the solution here, the general ones we could describe, so without any numbers, would be that Na is equal to Cl minus. So the acetic acid doesn't have either of those in it. That would be the acetate and an H plus. So that doesn't affect this Na or the Cl. And then generically, if we call it acetic acid A, then HA plus A minus is the total acetic acid, right? Okay, then more specifically, using this these formula weights given, we could say, well, then the sodium, which is also equal to the chloride, is going to be this 10 to the minus 3 divided by the 2 liters. So the formula weight then, that's going to be divided by 1 liter. And so if we do it in 2 liters, we have to account for that. Okay. So those are just going to be 10 to the minus 2 divided, 10 to the minus 3 divided by 2. And for the A total, we can say, well, the combination of HA and A minus, that's going to be the 3 times 10 to the minus 4 divided by 2. Okay. All right. Make sense? Okay. And by the way, these slides, you know, they'll be posted, and you can always skip, load them up and uncover the solutions as well. Okay, let's do another. Here we have 3 times 10 to the minus third formula weight of bisodium carbonate, or sodium carbonate, I guess generically, which can be represented as Na2B. We're going to place that in 2 liters. So again, this would, if it was in 1 liter, that would be 3 times 10 to the minus third moles per liter of initially pure water. Then for this solution, we want to know what are the general mass balance equations and the specific ones. And I'm going to remind you that since Na2, this is acting like that Na2B, we need to consider the H2B, the HB minus, and B2 minus. Okay. And if you can do this, we have most of the carbonate system covered. Okay? This is the fundamental piece of dealing with the carbonate system. So we can piece together from the different cases we've looked at. We recognize we have this amount of sodium that we add is 2 times the total B. So for every 1 Na2CO3, we get 2 sodium ions out for 1 carbonate. So that's the first general equation. Next step would be kind of what I was alluding to up here at the top. Those are the 3 species of B. There's no other forms of B once the Na2B has dissolved. So then the total B is in those 3 forms. Now, more specifically, we could solve and find that the sodium concentration should be 3 times 10 to the minus 3rd moles per liter. And we could then also say, well, that is twice the amount of B total that we have. Now, I think they have a typo here. They are doing something here that we don't need to do yet, which is accounting for the charge. This is something that we will get into with the electroneutrality equations, but we don't need to do yet. Right now, the general mass balance is the concentration of this plus the concentration of this plus the concentration of that. Once we get into the proton and electroneutrality balances, we are going to have to start accounting for how much of a charge they are. So I'm pretty confident they made an error here. I think even in their previous equations a few slides ago, they did not do that, right? But we will have to do that, so I'm just pausing us there. Yeah.
So I had originally put that 2 times the concentration of Na plus is equal to Bt because there was in the dissociation of Na2B, it makes 2 Na plus B2 minus, and so I was confused why just the concentration of Na plus is equal to 2 Bt.
Yeah, this is a good question, and it's always a little bit counterintuitive. So if you look at what I'm writing up here, if we dissolve Na2B, and this is going to be a one-way, right, just a dissolution, what we're going to end up with is 2 molecules of sodium and 1 molecule of B2 minus, right? And so it feels like that it should be 2 Na equals 1 B, right? That's what you're saying. But if we pause and say, okay, well, how many sodiums do we have? We have twice the number of sodiums as we have Bs at this point, right? And that means the concentration of sodium is twice as high as the concentration of B, right? And so then we have to say on a concentration level, because over here these are concentrations, the concentration of sodium is equal to twice the concentration of B. So that's where we can get caught up. Okay. Look okay otherwise? Good on that? All right. Okay, so let's elaborate on these alpha fractions, and we're going to derive kind of how we get a simple form of them that will allow us to solve lots of problems. And in fact, you've probably done some of this in the past, but this will be a bit more elaborate, and hopefully we can take it piece by piece and say, okay, here's really how things are connecting and where we're getting this final form of it. So I already mentioned to you alpha 0 is the form that has given up exactly 0 protons. So the form that is HA, the fraction of A total present as HA, right? So we talked about that. That means A1 would be the fraction that is A minus, fraction of total A that is in the form of A minus. And this is a fraction. If we multiplied it by 100, that would be a percentage, right? So we could say alpha 0 times 100% would be the percent that is HA. Okay, So you've seen all sorts of fraction to percent stuff. Just reminding you that 100% of everything from the mass balance we just had will be in HA and A minus. So if we did alpha 0 plus alpha 1, that should be 1. And which should correspond to 100% if we put it into percentage. Okay. Hopefully that part's makes intuitive sense there. Okay, so we can go up to alpha 2 or even alpha 3 if we have diprotic or triprotic. Here's the kind of the formal definition. The subscript is how many protons have left the acid. So we've got, with all those pieces together, there's some other mass balance kind of pointers that we can look at. And we could say that, well, that means the concentration of HA is going to be equal to alpha 0 times A total. Now, saying that is going to be really obvious, right? Just to say it out, it's, well, the amount that's in HA is going to be the fraction that's in HA times the total. But to have written it out is actually very convenient, and you might forget that that's something that you could just write out as an equation, right? Because that gives you another equation in our, when we're solving these problems to do the algebra. And we can also say A minus is going to be, the concentration of A minus is going to be equal to the alpha 1 times the A total. And I've already talked about this one as well. So these pieces here give us new tools to say, okay, how are we going to use this? And if we have a bigger equation that's more complicated, can we simplify it into here? And especially if we can get the alpha in terms of simpler terms, if we can simplify the alphas to reduce the number of unknowns, then we're really, as they say these days, that we're really cooking, right? We're getting somewhere with our problem. So if we can simplify this, you guys like that? Who knew? Chemistry. Okay. If we can do it to just K and H plus in particular, that's going to be really helpful. That will reduce the complexity. And in fact, what this is going to do is it's going to use some of those independent equations, and we're going to combine them in this particular step. And the next slide will do just that. That will make use of these multiple equations that we've derived or found to start simplifying, and instead of having the alpha fraction over here in terms of HA divided by HA plus A minus, if we can get that in terms of the equilibrium constant, which is telling us what kind of balance do we have between those, and the H plus concentration, which is the other piece that determines it, we have just simplified it quite a bit because we know K, or we can solve it, and H plus is very easy to find, or it might be what we are trying to find, okay? So that's going to be the target in order to get there. All right, so how do we do it? Well, I'm going to go ahead and put on the right here the generic equation for Ka for an acid. So that equilibrium constant is products over reactants, HA plus times H minus, A minus times H plus divided by HA. We can rearrange that if it's convenient, and we will see in a minute that it's going to be very convenient to go ahead and divide both sides by H plus typically. Sometimes we might invert it from there as well. So let's take a look at the alpha 0. Our initial condition is HA divided by HA plus A minus is equal to alpha 0. Well, if we divide the top and the bottom of this equation by HA, we can simplify a bit, right? So we can get the top to be 1. So I'm just going to say divide by HA. And we're going to do that to the top and the bottom. Since we do it to the top and the bottom, we're allowed. It's kind of like multiplying the top and the bottom by 1 or whatever. You know, we can multiply or divide top and the bottom. So when we do that, the equation simplifies a bit. So now we get 1 over 1 plus A minus divided by HA. Okay, you see that? And now it might make sense where this piece, it's a ratio of one to the other. It's the A minus divided by HA. It's not the fraction, but it is kind of close, right? We can recognize if I gave you, let's say, a few pieces of chalk that are sitting here, and some of them are colored, and I have a colored to non-colored chalk ratio of 2 to 3. I just gave you a ratio. There's two white ones to 3 colored ones or something. There's some ratio we could find there, and then you could think to yourself, oh, I can make a total out of that and get the percentage of a total. If I did 2 and 3 is 5, well, 2 out of 5, we can convert that, that's 40%, right? We could intuitively in our mind say there's from a ratio to a percentage. Well, we can do the same thing here with the fact that we have a ratio there can give us a connection to that fractional portion. Okay, so here's where our K can come in, because the Ka equation we simplified here can be inserted right here. Right? So what I'm going to do is I'm going to give myself a little more room, and then I can say alpha 0 then will be 1 over 1 plus Ka over H plus. Okay, and now we have it in K and H, which is exactly what I was talking about we should try to do last time. Am I too old to say cooking, by the way, to use it that way?
Oh, man, no.
We'll have a formal survey later. Okay. Now we can do the same thing with the alpha 1 fraction, but we'll find that it feels a little different. We can do the same simplification, divide both the top and the bottom by something, in this case A minus. And now we have 1 over 1 plus, and this time it's HA divided by A minus. So in this case, we need to flip the script a little bit. So we could simply say HA divided by A minus and just flip both sides, right? So the H plus over Ka. So then we insert that piece in here. And now our alpha 1 fraction should be 1 over, I'm just going to leave the 1 plus on this side, 1 plus H plus over Ka. So really it's just flipping that piece on the denominator. Okay, so this derivation is really convenient when we need to find some fraction of a fraction of something in a solution. Now, we've done this for the alpha 0 and alpha 1 fractions. That's for a monoprotic acid. We can do the same exact thing for a diprotic and a triprotic. It's just that the algebra gets a little more cumbersome, but it's the same thing, okay? So we will probably skip some of the algebra and just give you the equations. Maybe I'll torture you a little and make you do it on homework or something, but it's not something we need to do this process too much, because we can kind of have it on hand. Say, oh yeah, this is the equation for that alpha fraction, this is how it works. But I wanted you to see how this is working, right? How this is connecting the mass balance pieces plus that mass transfer piece, getting these equations together so that we can have a simpler or more direct result to work with. Okay, and of course the finished products here are just listed down below. Okay, any questions on that? Okay. So how are you guys feeling about MATLAB? Let me first ask, how many are you feeling uncomfortable? Okay, so about half of you maybe. Raise it a little higher if it's very uncomfortable. Or you don't have to admit it, I guess. Okay, how many of you are feeling are kind of comfortable? Okay. How many of you feeling kind of excited, like you really like this stuff? Not there yet. Okay. So I need to give you some challenges that you can overcome, and then we can do it. How many of you would like me to do a little MATLAB right now to illustrate this? I have a little script. Would that be good? Okay. So I've got this program up already, and this is something that you could copy and kind of do yourself if you'd like. And I'm thinking I'll probably give you an assignment sometime soon, probably not before the first exam. It'll probably make a little more sense with this second piece. You guys have had what, like three or four of the MATLAB learning assignments to do so far? Two? Okay, so we're just kind of scratching the surface so far. Okay. So maybe after the first exam, I'll give you a little bit of this to do. Because we're building into the graphical approach to solving things, what we've just done is basically built up the alpha fraction. And what I can show you right here is the alpha fraction they're being put in to right here with the water equation. Okay, so this will connect with that alpha in a moment. Let me just skip forward for a moment to make sure there's nothing else I felt like I really have to talk about before I spend 10-15 minutes on MATLAB. Okay, I think we can pick up here next time. Yeah. Okay. So I'm gonna spend a few minutes with MATLAB, and feel free to be on your computer with it or ask me questions or any of that. So in this problem, while it loads, I'm just going to say essentially what we are. There's a couple things I'm showing you. One is we can get some sort of input prompt to I think maybe I showed it to you, but MATLAB, we can write a code to say, let the user input the value you want. So if I want, this thing will tell us, okay, tell me what is the pKa, right? And that'll allow us to this is strange. I'm getting these little prompts for my different apps to want to access my location, and no, why? All right, so let me just explain real quick. This script that I'm going to talk through and show you is going to plot some fraction of HA versus A minus. I said water. I lied. I'm sorry. This is not for water. I have that in a different thing, and I think I already showed you that. So this is basically the HA versus A minus. And so what I might want to do is plot as a function of pH going from 0 to 14. Maybe I want to plot the amount that is in one fraction or the other. So I could say the concentration of A, but I'm going to put so A minus or HA. Okay? So the concentration of whichever species. And if I think about it for a moment, I'm gonna specify here for a second that it'll act like water, where this is our Ka. So if that's our water, if that's our Ka, kind of somewhere in the middle, most of the acidic condition, we should have more protons, right? So there's more protons around, so we should have the more protonated version of our acid. That means we should have a lot of HA over here and then it'll start to decrease as we get over towards a more basic condition. So this one should be HA, and then conversely, we should have more A minus on the other side. So that's what it should look like, and we could certainly do that in Excel and calculate each of those and plot that. But I'm going to do this, or I have already done this in MATLAB, and I want to show you kind of what that looks like a little more clearly, I suppose. Okay, that's long screen. Okay, so I have this program. I've named it AH versus A minus. So basically in the PowerPoint, I just had copied over this exact stuff. And you could open these even in a notepad if you wanted to. And it'll look a lot like what we saw here. This is just me opening it in Notepad. Okay, so let's start by just seeing what happens when I run the program. And then you guys tell me if you want me to kind of do anything different or answer any of your questions. Be happy to do so. But I'll kind of walk through what's happening in the program piece by piece is probably what I'll do. So let's run it first of all. I can either run it by clicking the start button or typing in the command here, assuming I'm in the right location. I think I am. I can type the name of the program, AH versus A minus, I hit enter, and then it runs. And so it's asking me, what is the pKa value? The reason it's asking me for that is because I coded it to say some variable Ka is set equal to 10 to the minus, and then in parentheses, input, and then that's going to take whatever input response I give it, and it's going to give me the question that I put in the little quotations. So it's going to ask me this, and it's going to take the answer to whatever I write there and put it into the equation. Okay, so it's going to grab whatever I put in and stick it in there, and then the Ka value will be 10 to the minus whatever I just put. So what is the pKa value? What do you want it to be?
4.
All right, we've got 4. I hit enter. So Ka then is 1 times 10 to the minus 4, kind of obviously. And then it's also going to go on, it's going to do some calculations. Basically, you can think of it as setting up a few Excel columns of the HA and the A minus versus pH. And then it's going to plot them. And it's already done so, but it has put it on my screen instead of yours. So here's the result. And what I have here is I've got it in 2 plots. One is a fraction, 0 to 1, and the other is a log plot for the actual concentration. So I've told it to plot in these 2 different ways, and sure enough, we look at 4 was the pKa, and that's exactly where each of them are equal. That's the equilibrium. Well, that's that's our equilibrium point. That's the spot where they are equal. Now, of course, we can find equilibrium where they're not equal. We've talked about that. But if pH is 4, they are both the same concentration. Okay. Let's do it again. Different pH. By the way, you can press up and down arrow keys when you're in the command here and sort through the previous things you've done. So I can run the code again. Somebody else give me a pKa value. All right. And basically we're doing water now, and it plots it right at 7. Now, I have no idea, but I had a random idea. What happens if we do it again but give it 25? Probably Okay, it didn't break it, that's good. But we see we don't really have any amount of, we'd have to get to pH 25 before we get some of the basic version of it, or get half of it as the basic version. And likewise, we could actually do that for essentially -3 is HCl, right? And so this is the reason we don't have much HCl if we add it. It completely dissociates because we'd have to reach pH -3 before we get an equal amount. So there's very little amount of actual HCl. So if we add sodium chloride, there's not really that much hydrochloric acid there. Okay, so let me walk through a little bit then the script itself. And by the way, we can open this in its own window or pop this out. Should be able to, or maximize it. We could even put a separate script over there if we wanted to. There's different things we can do to just arrange our workspace. Okay, so the first little bit is just kind of nonsense. The percentage sign means it's a comment, and I'm just commenting on it. Doesn't matter. Then I've got clear and CLC. This is maybe good practice, probably doesn't matter too much. And what I can say is this, I can put a comment here, clears variables, in case there were any left over, and this guy clears the command prompt in case we needed to. Usually these don't matter too much. Next up, we have the KA. We're defining it. We're defining a KA value based on what the user wants to put in, right? So I might give you a homework where I tell you, write me a script that you ask me for a pKa value. I get to put it in and test to see how your code works, right? And then submit the graph that it puts out. And that's a good way for me to see, okay, well, what does it look like when it runs? Does it run? Is it set up properly? I would just need to open it up and try it. Okay, so then next up, I defined a pH range from 0 to 14. This is kind of like in Excel, you might take 14 rows, or you might say, okay, I'm going to do 14 rows, but I want more than 14 because I want to do every 0.2 or 0.5. So I'll go 0, 0.1, 0.2, and do that, and have 10 times 14, so 140 rows, and do it by every 0.1. So that's what I've done here. If you just did, and I'm going to come back to this, if I had said a pH range is going to be equal to 0 to 14, that'll give me, by every one step from there. But I could say pH is equal to from 0 to 14, but I could add another little semicolon here and say by every 0.5, and that's going to give me by every half. Now that's just a little piece of syntax or stuff, how you make an array. I think that's probably the type of stuff that will be covered in your stuff if you haven't seen it. Don't worry too much about it if you didn't know that. That's just a little piece. There's different ways you could do it, right? You could even just say pH is equal to 0, 1, 2, etc., right? Okay, so that was not the right way to do it. That's not proper syntax. I think the comma might not be right. Or maybe I just need the brackets. So you could just do a space. If you do brackets instead of parentheses, then each number, right? So you could do that manually. That's not a big deal. Yeah.
So like earlier on, I was trying the code where I was just trying the function where I could like generate random pH values.
Okay.
And so I tried like so many different ways, and a lot of the random functions just didn't seem to like do that. And like one in particular was it returns a value between 0 and 1.
Yeah.
And so I had to kind of do it like a bootleg way where I did a pH range between 0 and 13 and then added the random, 0 to 1 value.
Yeah.
Like, it ended up just, I was just wondering if there's like a quicker way to do it.
So it's a very good question there, and I'm going to answer this for everybody, and then we'll close up shop. So, in case you didn't hear, the question is like, what if I wanted to generate a random number from 0 to 14? Well, my first instinct here is to say help rand, in case that's a random function, right? So I can look into the MATLAB's help and see what's there. There probably is. I could also go to Google, but let me answer the question, because you were saying you did like a bootleg version where you said it could do a random number from 0 to 1, but I wanted 0 to 14. So maybe MATLAB has a way to do it and define that. Or what you could do is take that random fraction from 0 to 1 and simply multiply it by 14. And that'll put you between 0 and 14, right? Mind blown here. And so sometimes you do want to bootleg it. And that's actually a pretty good way to do it. And there's actually a lot of interesting theory in the computer science world about the random number generation. How can you make it truly random? Is there patterns involved? Does it depend on your clock on your computer? Or how are you getting a random seed? Because a lot of times there's like a table and it's just picks a spot and calls it random. So there's a lot of interesting things there. So one way to do it is have a big table of random numbers between 0 and 1, and then look at the time on your clock and say, okay, well, if it's that particular time, we'll select that one. And so some of them are not true random, but anyway, so there's a lot of interesting stuff there. So yeah, I'll leave it off there. So it sounded like you guys like this, so I'll try to do a little more of this in the future. All right. Why not? It's at most 1.